Bernoulli's equation is one of the more difficult concepts to intuitively understand on the entire MCAT. First, let's look at Bernoulli's equation and explain what each of these terms means, and then we'll look at some examples to help you develop a better conceptual understanding of it and see how you can apply it. Bernoulli's equation is only applicable to fluids that don't have any turbulence and are not losing energy due to friction. And if those two conditions are met, what it's telling us is that at any 2 points in that fluid, the total energy is conserved. And each term on each side of the equal sign is a form of energy in either of those points in the fluid. Capital P is the pressure energy. So pressure is basically a form of potential energy. And this term is just telling you at this point, how much pressure is this fluid under? So imagine if you were able to put your hand at that point in the fluid. It's basically describing how much pressure would your hand be feeling. So for example, at this point here, you're at a greater depth, so you're experiencing a higher pressure, so the pressure energy for that point would be higher. But again, we'll look at some more examples to explain each one of these more in depth. The next term, 1/2 rho v squared, is used to describe basically the kinetic energy of the fluid at that point. Rho, or what looks like a lowercase p, is just the density of the fluid. And then v is the velocity. Hopefully this one's easier to understand why that one's describing the kinetic energy, since we're using velocity in that term. And finally we have rho gh. Again, rho is just density, g is the gravitational constant, and h is the height or the distance from the ground. And the reason it's height is because what this term is the gravitational potential energy for that point in the liquid. Make sure you never confuse this with the depth under the surface of the water. So for example, we are measuring the height of this point from the ground. We are not measuring the distance from the surface of the water. And some of you might have the equation for hydrostatic pressure memorized as rho gh. If you're doing that, h is referring to the depth, but it does not refer to depth when you use those letters in Bernoulli's equation. So now let's see how to apply this to some examples. We're going to look at how to apply Bernoulli's equation to these 3 example scenarios. And one of the things that we're going to be focusing on with each one is finding terms to cancel out, because that's one of the most common things you can do whenever you have to apply this equation on the test. Starting with the one on the left, we're going to compare a point at the top to a point at the bottom. And what's unique about this situation is that this pipe has a constant cross-sectional area. We then want to apply the continuity equation, which is a really common thing that you want to be thinking about whenever you encounter problems like these. And what that says is that the flow at point 1 equals the flow at point 2. And flow is equal to the cross-sectional area times the velocity of the fluid at that point. So A1 times V1 equals A2 times V2. And what's important about that is that since these areas are equal, that means that the velocity has to be equal at those 2 points. So then our kinetic energy term in Bernoulli's equation on each side is equal, and that means they cancel each other out. So our equation becomes much more simple once we cancel those out. And the next thing you can do to make this equation even more simple, and this is something you can apply to any Bernoulli's equation, is to take the lower height and set that height equal to 0. And then the higher height, you can set that equal to the difference between the 2 points. And we'll say that is delta H, or the difference in height between point 1 and point 2. Let's say that the higher point is point 1 and the lower point is point 2. What this allows us to do is cancel out rho gh2 because h2 is equal to 0. And for example, if there's a difference of 12 meters between these 2 heights, then h1 would just be equal to 12, while h2 is equal to 0. That's regardless of what the actual heights are. What we have now for Bernoulli's equation is much easier to understand. It's saying that the pressure at point 2, so this term here, is equal to the pressure at point 1, so this term here, plus rho gh, and again, we said that h is the difference between those 2 heights. And intuitively, all that's saying is that the pressure at point 2 is the same at point 1 plus whatever pressure this column of water is exerting onto it. So if you have a situation like that and you can get to this point, it makes the problem much easier to solve. In the next situation, we have a pipe with a large area that gradually decreases until it has a much smaller area. We'll be comparing a point on the wide section of the pipe and one at the narrow section of the pipe. And if you look midway at the pipe at those 2 points, you can see that they are at the same height. So h1 is equal to h2, which means that the rho gh term is equal on both sides of the equation, and that makes us able to cross them out. Now, once again, we're going to apply the continuity equation here. If a1 times v1 has to equal a2 times v2, and let's say that this is point 1 and this is point 2, then since the area at point 2 goes down, that means that the velocity must increase. So the velocity at point 2 is greater than the velocity at point 1. What that allows us to see is that since the velocity over here is greater, this entire term is going to be greater. And if the kinetic energy term on the right side is larger than its counterpart on the left side, then the pressure term on the right side must be smaller than the pressure term on the left side. So this proves that when comparing 2 points of a liquid that are at the same height, if the velocity increases, the pressure must decrease. Now let's look at the last situation. And with this situation, we have a large container of liquid that then has a small opening, like a hole at the bottom. And then liquid will be able to flow out of that hole. So we are comparing a point at the top of the liquid that we'll call point 1 with the hole at the bottom of this container, which we will call point 2. Now we look for things to cancel out. We can set point 2's height to 0, and then the height of point 1 is going to be equal to delta H. Since H2 is 0, we can cross out that entire term. The next thing we can do to simplify the equation is to compare the velocities. The fluid's velocity at point 2 is going to be pretty fast because the liquid is leaving out of a small hole in this large tank of liquid. And the velocity at point 1 is referring to how fast is the water level dropping. And since this is such a wide tank, the water level won't be dropping that quickly since the water can only leave out of the small hole at point 2. What this allows us to do is set the velocity at point 1 approximately equal to 0 since it's pretty much negligible compared to the velocity at point 2. So this gives us another term to cross out, which is 1/2 rho v squared at point 1. So we've already simplified our equation to this, but we can simplify it even further. When comparing the pressure at point 1 and point 2, the pressure at point 1 is just the atmospheric pressure because there's nothing else pushing on the liquid except the air above it. Now the pressure at point 2 is where things get a little bit tricky. It's tempting to say that at point 2, it is feeling the pressure of all of the liquid above it. And if there was no hole in the tank, that would be true. But since there's a hole in the tank, it's actually not feeling that pressure from the liquid above it. So what that means is that the pressure at point 2 is just the same pressure at point 1, it's only the atmospheric pressure. So since point 1 and point 2 are equal, we can cross out both of those terms and we end up with a very simple equation. If you can remember how to simplify the equations for these 3 scenarios, then regardless of the specific question you'll be given, you'll have a strategy to make it a much easier problem to think about and get a correct answer.